Hi, and welcome to the completion of the first lecture. This is the lecture intended for the ninth period class, so that's the second class I teach during the day. And I'm picking up where we left off, which was at the end of page 2. I wanted to note, so at the end of this, we had just derived out the optimization problem for Farmer Jones. And one of the things that I didn't talk about, so let's talk about it now, is parameters. So we have constants in the model. And remember, those would be any quantity, any fixed quantity during the solution, during the solving of the model. Okay, so in this model, the $3 or $4 of profit, that would be considered a constant. Okay, so what is a parameter? A parameter is a special type of constant where that is represented with a symbol. Now, you might think, well, why is that? Okay, so suppose Farmer Jones was experimenting. I should probably spell symbol correctly. Farmer Jones, suppose he was experimenting with different recipes for his chocolate cake or his vanilla cake. And maybe in that he was trying to see, well, what happens if I change the amount of flour I use? So he might replace the 4 and the 6 here with parameters. So instead of the 4, he might say, well, let's let F C equal amount of flour in chocolate, and F V equal amount of flour in vanilla. These would be constant while we were solving the model. Okay, so we would replace this line. It would look like a FCC plus FVV. And before we were to solve the model, we'd have to understand what the values Farmer Jones decided to use for those. This kind of model would now be called a parameterized optimization model because one or more of the constants are parameters. Okay, so you just need one. And if you think about it, a parameterized model is very powerful because it generalizes a given optimization model from one, what we call instance of the model, to infinitely many instances. Because even if you have one parameter, you could change that to any one of an infinite number of things. Now, before you solve it, you have to know what it is. So parameters, one thing I want to emphasize here, parameters are not decision variables. Okay, so keep that in mind. Okay, oopsie. I clicked on the wrong button there. Okay, sorry about that. Let's move on to the next slide. Okay, so some other definitions. Again, these are all in handout 1, so that'll be part of the work you do. So I'm recording this video, right, because I'm going to be have a substitute, Professor Svirsko, on Tuesday. And I'm going to have, what you'll be doing there is she's just going to put you into breakout rooms, and you're going to work on handout 1 and also some of the work from lecture 2. Okay, a feasible solution to an optimization model is a choice of values for the decision variables that satisfies all constraints. The feasible region is a collection of all feasible solutions to the model. The value is its objective function value. An optimal solution to an optimization model is a feasible solution whose value is as good as the value of all other solutions. So for example, in Farmer Jones, this would be say a C star V star pair such that, well, its objective value, so that was 3C star plus 4V star, would have to be greater or equal to 3C plus 4V for all feasible CV pairs. Okay, so if you look back at this model, the objective was 3C plus 4V. So that for C star V star to be optimal, it would have to be greater or equal to any other CV that satisfied these constraints. Okay. Note that it doesn't mean, it is not true that you can say that such a solution, such an optimal solution, would be unique. There could be others. Also, please note that we have to be very careful when we talk about this is the value of C star V star, and that which is a solution. Okay, so differentiate in your mind between the solution to an optimal optimization model and the value of the solution. Okay. Okay, so we classify based on characteristics of the decision variables, constraints in the objective function. Decision variables are either continuous or discrete. We have that a function can be linear, and in this case, it's a constant weighted sum. So you're given these, in this case, remember, these are parameters, C1 through Cn, constants. And then you weight each x1 through xn respectively by their corresponding constant, and you add that. All linear functions can be written in this form. Otherwise, a function is nonlinear. So let's just see it here. Here, is this function linear or not? Yes, this is linear. In this case, C1 equals 9. C2 equals negative 17. Here, no. 5 divided by x1 is not linear and can't be expressed that way. No again. This is a fraction. Fractions of polynomials are not linear. And here, no. Products of variables are also not linear. You have to be careful when you have parameters, right? Because parameters, they are also represented by symbols, but they are not variables, so they can be multiplied. So let's say if you were given like parameters C1, C2 times x1, this is still a linear expression. And we would say this is linear in x1. So often, if it's unclear from the context or unclear in the problem what is a decision variable and what is a parameter, you can ask me these questions. If sometimes it's not specified. For example, in the examples I have here, it's not given. Oh, by the way, this should say parameterized. Abstract and concrete are last year's term for it, but we are going with a more usual parameterized or not. Here, it's not given what the decision variables are. So it would be very fair of you to say, hey, what are the decision variables in this model? And they are the decision variables are Z1, Z2, and Z3. And here they are W1, W2, W3. Okay, so let's now answer these questions with this in mind. So here, and if you want, you can pause the video and see if you can guess yourself. So go ahead and pause it if you'd like and try to answer that. I'm going to go on now and answer it myself. So here, this is indeed a linear program. I can see the objective Objective and constraint functions are all linear. Also, and this will be a subtle point that I want you to be aware of, they're all weak inequalities. They're all greater or equal to or less than or equal to. There's no strict inequalities. So this is what I mean with strict. Okay, so it's a linear program. If it had these cannot be in a linear program. Okay, is it parameterized? Well, let's look at 3, 14, 7. Nope, those are all numbers. They're not symbols. 10, 5, 25, negative 18. Nope. No, just one. The coefficients here are 1, 1, 1, and the final 3 constraints, so not parameterized. Okay, here, let's look at this. Let's see, C is a given constant. That should tell us this might be parameterized. And indeed, let's answer that question first here, because in the very first line, you see 3W1 plus CW2 minus W3. This is, C is a given constant, which means, and it's used, so it's a parameterized. Is it a LP? The first constraint function, the objective function is, this first constraint is, but already we have a nonlinear function here in the decision variables. This is linear, but integer. This is a discrete variable. This cannot be, we have to have continuous variables in an LP, so it's not an LP. Farmers-Jones model, if you go back and look at it, you should convince yourself that the thing we wrote in the boxes, not when I describe what parameter is, but the things in the boxes is indeed not parameterized. And it's an LP, it's a linear program.